Well, greetings, everyone. I'm pleased to be here. Cambridge was lovely yesterday. Not exactly as I remember it. I'd like to talk briefly about mostly the ocean. It's a short time, so I'd like to bring up essentially ideas to do with eddy activity in the ocean that seems to be important for the larger general circulation and issues related to climate change and climate itself. As I said in the abstract, the angular momentum of the solid Earth is inherited by the fluid oceans and atmospheres and fragmented into potential vorticity, and even down at the scale of hurricanes and tornadoes, the Earth's rotation is strongly felt. Most tornadoes, something like 90%, are cyclonic, and there are sources and sinks working along the way, but it's an amazing control of the solid Earth on that fluid, on those two fluid envelopes. Some of the dynamical problems for which turbulence is essential. What I'd like to try to outline today has to do with nonlinear Rossby waves in the upper ocean. The deep, excuse me, is there a pointer, Jim?
Yep. This one.
Oh yes, good old-fashioned pointer. The deep branch of the meridional overturning circulation, which is sometimes called, rather erroneously, the conveyor belt, and revisiting the deep western boundary currents. And a third example, the upper branch of the meridional overturning circulation and penetration of warm waters poleward and pervasive influence of the freshwater cycle on ocean climate. There's a lot else going on in the field, which probably won't come up this week, but turbulence of all scales is highly relevant to global energetics of the meridional overturning. Are strongly under debate at present. Basic questions: where does the water circulate upward? What rules the creation and flow of deep water masses? What are the relative roles of mechanical and buoyant forcing? But that's for another time to talk about. Well, as is widely known now, the mesoscale or synoptic scale of geostrophic turbulence in these fluids has life cycles which are to some extent predictable. Expansion of scales when turbulence is free to evolve, vertical alignment, barotropization, and concentration of PV into isolated cores, and acceleration, radiation of various wave modes. The interaction with the large-scale circulation through flow instability and wave radiation, basically highly under the control of potential vorticity. The way in which the eddies shape the general circulation, redistribute, concentrate, dilute, extend, and this is beginning to be understood through episodic stirring and mixing of potential vorticity. And finally, nonlinear propagation of finite amplitude waves. The waves, as Michael McIntyre always likes to say, the wave turbulence jigsaw puzzle is always with us, and particularly so when we realize that the potential vorticity has the inherited scale of the planet, and yet also the fragmented scale of the turbulence. And so the nonlinear wave propagation is always lurking in these problems. For the ocean, we're forced primarily at the upper surface. By the way, am I loud enough for everyone? So good. Okay, I can't hear an echo. The ocean is forced primarily at the upper surface. Eddies provide one of the mechanisms of pumping the energy downward through the form stress component of the potential vorticity flux, as well as through purely barotropic pressure fields. Microscale turbulent mixing is essential in closing the overturning circulation. Well, a sketch of the oceans that was relevant for today looks a little bit like this, with a sea surface at the top and isentropic surfaces, constant potential density surfaces, which touch the surface or touch the upper turbulent mix layer along what are called outcrop lines, and then they descend. These stable surfaces descend into the ocean interior, and along these surfaces one subducts, as the terminology goes, subducts fluid out of reach of direct atmospheric forcing, submerged beneath stable stratification, to live a long and fairly uneventful life down there without very much external forcing. So I'm going to emphasize observations really, and circulation models and observations and lab experiments have all reached a new level of accuracy in recent years and actually can now talk to one another, which I think is quite a new event. Within the last 5 years, we have for the first time a global observing system for the oceans consisting of satellite altimetry, which sees the surface elevation, and drifting buoys, many of them, which see the surface circulation and measure temperatures and atmospheric pressures. And now, by now, 3,000 subsurface Argo floats, which are dotting the world's ocean and giving subsurface hydrographic temperatures and salinities and things to do with biology as well. In addition, observations with new technologies are targeting special regions, robotic sea gliders. This is a sea glider from University of Washington, and it looks a little bit like a narwhal, which is an instrumented whale operating in very similar parts of the high latitude oceans as our sea gliders. Along with these must be mentioned, articulate chemical tracers, purposefully introduced SF6 and inadvertent tracers like tritium CFCs and iodine 129. Well, Dudley Chelton has done a wonderful job of taking the Topex Poseidon and European satellite altimeter data and using it to illustrate the geostrophic turbulence / Rossby wave activity of the upper ocean. This is what you see with one satellite, a snapshot of the sea surface. I'm sorry, probably the seeing here is not terribly good with this projector, but this is with 2 satellites. You see you suddenly resolve much more fine detail down to a couple of 100 kilometer scale. A long track resolution for this instrument is more like 30 to 40 kilometers, and we are seeing clearly the slightly larger than mesoscale eddy field of the oceans with this. There's hope of the SWOT SWAT satellite altimeter array to be launched in something like 2014 to 2016, which will improve these resolutions by an order of magnitude. This is the animation which should make Julian Hunt happy to see this is 1994, time going by very quickly. Animation of the sea surface elevation perturbation field. You see Kelvin waves and Rossby waves zipping along the equator with very large scale. We passed through the 1997-98 El Nino quickly there. Should cycle back through it. But the thing that you see, this video could occupy the entire day if we talked about the bits and pieces of it. Basically, we see variability drifting westwards almost everywhere in the picture, which sounds like baroclinic Rossby waves at the surface, and no doubt is related to them. And tropical equatorial events, which are very well resolved. At higher latitudes, the resolution is, the Rossby radius decreases, and so we're missing some important detail. But generally speaking, you can see the strong westward push of phase motion in this picture. Even the Kuroshio and the Gulf Stream, which are flowing rapidly to the east, are barely making a visible eastward progression of eddies. This is about the only site. The greatest of ocean currents in the world is the Antarctic Circumpolar Current, and you can see it persistently pushing phase eastward. The other thing, there's some very subtle features here which may not be visible to you, but there's an annual Rossby wave which comes off the west coast of the US, for example. You might just be able to see that. Local investigations with our sea gliders make it very much clearer, and indeed local investigations throughout this domain have looked at this same variability in great detail. And the westward phase propagation here plotted with time increasing upward and against longitude is very clear in these patterns. And as in Chelton's and collaborators' work, the westward phase speed is not far from a very simple reduced gravity model or first baroclinic mode model of baroclinic Rossby wave propagation, slightly in excess of that, which has led to a feeding frenzy of theoreticians to explain with things we've known for years, such as the role of rough bottom topography in expanding the vertical scale of the eigenmode and making it go a bit faster. But I think that may be somewhat less relevant than the fact that these are really nonlinear structures. And Shelton et al. In GRL recently have very strongly emphasized that, for example, a symptom of that is meridional migration of the cyclones poleward and anticyclones equatorward. If you remove energy from a vortex structure and without destroying its PV, it should try to find its rest latitude, and that's as hurricanes move poleward. Well, this is there was a precursor to all of this. Jim McWilliams and I are probably the only ones in the room who remember this experiment, but the global structure at the sea surface is a beautiful thing, yet we need 3D information beneath the surface to say anything more about these structures and their turbulent nature, if it is indeed turbulent. And in 1973, the MODE, Mid-Ocean Dynamics experiment, followed on the Russian Polygon experiment, and for the first time investigated the three-dimensional structure of a few of these strong eddies. This is a time series in the western Sargasso Sea between Bermuda and Miami of temperature at many depths, 389 meters down to 5,348 meters, showing one of these large warm anticyclonic eddies moving across a rigid mooring site, a fixed mooring site. And this is over a period of typically 100 days. The velocities that go with that kind of activity were seen in the MODE project here. These are stick diagrams of vectors plotted against time. Again, you probably won't be able to read the axes, but this is a period of a year between here and here. And these are upper ocean, mid-depth, and deep ocean. And if you really looked hard at that figure, if I blow it up a bit, you'll be able to see that as one of these vortex structures moves by, there seems to be a deep ocean response somewhat in phase very frequently, but then higher frequencies ensue in the deeper water, as if something like a barotropic mode beneath the baroclinic upper ocean core has been excited. And this is quite consistent with very simple two-layer models of the dynamics. This is Chassinier and Cushman-Rosin talking about a two-layer model of a cyclone and here an anticyclone, in which the upper layer and lower layer stream functions are seen to evolve with increasing time up to 140 days from an initial simple cyclonic vortex. And the interface, the temperature field is plotted in the first column here. But what you see as the cyclone drifts westward with something like the correct Rossby wave speed, a little bit slower for cyclones, a little faster for anticyclones. The deep layer sees the excitation of a fast radiating Rossby wave mode. And so this is the character of solitary vortices on a beta plane. The migration of cyclones and anticyclones poleward and equatorward, respectively, is also seen there. And of course, now we have the capability to go much further with modeling resolution. The Japan Earth Simulator model, OFES. This work by Moto Nakamura and colleagues looks at the similar region of the western Sargasso Sea. And here we see the potential vorticity at 4 depths from the upper mixed layer down to 3,000 meters. And vortex structures, the potential vorticity is embedded in these eddies, is drifting along with these signals, and more and more accurately, I would say, the ocean models, while they are challenged to reach out to the time scales of the meridional overturning circulation, at the shorter time scales of intense eddies and wind-driven circulation, they seem to be doing extremely well. Tracers are embedded in these vortex cores, and so there's this feeling that these are vortices which are carrying fluid. And I have a video, but I think in the interest of time, I probably will just have to, it means getting out of PowerPoint and showing a QuickTime video. I'm afraid I'll have to leave that. But Dudley Chelton has made a wonderful video in which the chance occurrence of neutrally buoyant Rayfus floats seated off the California coast demonstrated that that these vortex cores, in many cases, are indeed trapping fluid and carrying them westward. Well, this has been well documented with the extreme events of ocean eddies many times in the past. But I think this a new feeling that more and more of the upper ocean is dominated by this strange mode of fluid transport in essentially nonlinear baroclinic Rossby waves. In the laboratory, we do these same kinds of things when possible. These are laboratory experiments in which a towed circular cylinder is moved around the fluid, in this case cyclonically, in this case anticyclonically. And I'm sorry the resolution is fairly hopeless here, but using a method we call optical altimetry, we can image the entire pressure field, the elevation of this fluid's upper surface to within about 1 micron, and that gives us the velocity, pressure, surface height, and potential vorticity fields quite accurately. And in this experiment, we're able to examine in some detail the wake of a cylinder, which of course has transitions between vortices and Rossby waves depending on the direction and magnitude of the cylinder's motion. So the vorticity for eastward and westward translating cylinders is shown here from this laboratory experiment. The dark cyclonic vortex cores have migrated poleward in cases either of eastward or westward, that is to say cyclonic or anticyclonic movement of the cylinder about in this polar beta plane. I didn't explain that this is a parabolic free surface beta plane, a one-layer fluid in which the North Pole is at the center. So the cyclonic and anticyclonic pairs, which are starting out in the normal Kármán vortex street configuration, are split and migratory in this way. Of course, if you go in the other direction, the cyclone has to jump over the anticyclone because it's on the wrong side of the street, so to speak. It's equatorward of the anticyclone, and so these actually jump over and swap positions and move forward. So we do this on this polar beta plane, which is using the virtue of the parabolic free surface of the fluid, and the measurement scheme here is an optical altimetry, which is using the surface as a Newtonian telescope. I'm happy to be in the home of the inventor of this telescope. In an environment with significant large-scale PV gradients, the geostrophic eddies excite mean circulation in many ways. Eddy PV transport expresses the rotational part of the forces of eddies on the mean state. And also we have radiation of what we call beta plumes. This is an animation of a source of low-density fluid on top of a high-density fluid on this polar beta plane. And you see radiating westward is a confused gyre, a cyclonic gyre, which is known as a beta plume because it resembles a low-frequency Rossby wave. But you can see it's highly unstable. And the beta plume produces many interesting things, mesoscale eddies and unbalanced internal waves. And basically, by the way, these are surface displacements between a micron and a millimeter of this laboratory experiment. But this is a more direct way in which eddies and mean circulation relate. This is from that same experiment, an illustration of radiation of internal gravity waves from the anticyclonic instability regions of this beta plume. This is a Hofmüller plot of time and radial distance, showing the very high frequency internal inertial gravity waves radiating in that way. Well, so water parcels can move with eddies and form essentially a novel method of general circulation. These are the first view that we ever had of the deep ocean doing this kind of thing in the drifting floats of the mid-ocean dynamics experiment. And the great excursions of these floats, this is 500 kilometers between these two tick marks here. The great excursion, I think, surprised us all and was evidence that although potential vorticity is in control in some sense, the fluid, given sufficient energy, can make wild excursions north and south. But this property of carrying fluid is really turning into very interesting new directions. Phytoplankton growth is concentrated in the upwell domes of westward propagating Rossby waves. This is the Hofmuller plot once again of time and longitude showing westward propagation near Hawaii, and Nicholson, Emerson, and Erickson using one of our robotic sea gliders instruments, which is that kind of instrumented sea lion, robotic sea lion, finds that phytoplankton, bursts of phytoplankton growth occur in the upwelled regions of these eddies, and very likely are transported with them, and that's established by the phase relation between oxygen and phytoplankton intensity. So we move into biology as soon as we get into Lagrangian fluid dynamics. Well, the global portrait of all of this eddy activity is usually given as a map of the time mean eddy kinetic energy. These are two versions of it here, one from satellite altimetry of the sea surface, and one from purely independent means, which is sea surface drifting buoys. There's an equatorial concentration in the western boundary currents as expected, concentration in the dominant path of the Antarctic circumpolar current. And these kind of supernova events are impressive, but one should not forget that eddy activity is virtually ubiquitous in this, on this Earth. And I'm going to skip forward a little bit to show this figure, which is the ratio of eddy kinetic energy to mean kinetic energy. This, in this case, from the Earth simulator runs of Nakamura and Kagemoto. But despite the relative weakness of eddies far from these boundary currents, the ratio of eddy kinetic energy to mean kinetic energy is even larger in these quiet regions, numbers between 100 and 500. So in some sense, the Peclet number of these circulations, the effective Peclet number, UL, a scale, horizontal circulation velocity, times a length scale of the whole ocean gyre divided by a Lagrangian diffusivity of fluid particles. That effective Peclet number is typically 3 to 5, which says that the ocean is quite diffusive, and even in those far reaches. And so if we look at a tracer like chlorofluorocarbons injected from into the sea surface, in this case in the Labrador Sea, they're moving on this potential density surface in this work of Smethy, Fine, Deborah Labelle and collaborators, moving southward in the meridional overturning circulation. And what you notice is that they're not moving in tightly constrained boundary currents the way the conveyor belt oversimplification would ask you to believe, but they're rather diffusively spread across the entire western side of the ocean. So this is the Al Gore and Willie Raleigh Broker has to take the blame for this, and it is a useful simplification for talking with simplified people. But a better version of it from Greg Holloway looks like this, which has warm and cold branches and admits to recirculation in major gyres, and it has connections through the Arctic. But nevertheless, if we look in a region where we expect a strong western boundary current carrying deep waters in the meridional overturning southward, we see something that's reminiscent of the earliest eddy-driven recirculations, which were seen in the early models of Bill Holland, in which the top, middle, and lower layers of the ocean showed wind-driven circulations, which were simple and straightforward in the square box world, and eddy form stress from the thickness flux part of potential vorticity flux would drive these deeper circulations. And those circulations tend to be scrubbed out and homogenized in potential vorticity, or let's just say very highly restructured, reorganized in potential vorticity. And when we look at the Earth simulator runs, which is now at much higher resolution, we see the same features in much greater detail. And we see ramps of potential vorticity. That's the planetary increase northward. And we see north-south guideways, and we see plateaus of potential vorticity at these levels from the surface descending downward through the ocean. So at higher resolution, and indeed when we first mapped potential vorticity, it was like falling off a log, because the stretching component of potential vorticity is dominant for these scales, and so it's just plotting F over H, the ratio of Coriolis frequency to isopycnal layer thickness, isentropic layer thickness. So this could have been done a century ago, but it was really only done in the last few decades to understand this key field. But the result, which Susan Lozier, hi Jim.
Hi, Glenn.
Oh, yes. The result, which Susan Lozier has made very clear, is that these PV structures, which are generated by form stress from the intense eddies overhead, lead to tighter circulations. I'm sorry, I should explain this more carefully. This is the roughly 600 meter depth layer, a potential density of 27, circulation and potential vorticity, and then a deeper layer, roughly 2,000 meters, where the circulation and potential vorticity are now highly constrained by latitude in the spirit of the early Holland models, but different in some detail, but with this nice plateau of PV sitting under the Gulf Stream. And this is just the structure which takes that conveyor belt image and spreads it out into a big schmozzle of Lagrangian particle tracks. So these are both synthetic and real neutrally buoyant particles launched east of St. John's, Newfoundland, and they should, by rights, travel down the western boundary current carrying Labrador seawater with them. But you see what they do is turbulently they're spread out to the edge, the flanks of the mid-Atlantic ridge to fill out this entire region. And so the CFC image was correct, and now we have direct images from Amy Bauer's Rafus floats launched near Orphan Knoll here, which show that only one single float out of 40 followed that deep western boundary current track. The dynamics is there, but the Lagrangian connection and continuity is not there. And so we have tightly nested recirculation gyres, which are one after another spreading the world's chemical tracers through the meridional overturning circulation. So I think these are this diffusive view of the circulation produced by mesoscale geostrophic turbulence is a wonderful part of the ocean, and I think the story continues as we visit the many branches of the circulation. Both mesoscale eddies and microscale mixing are shaping the flow and the properties of major water masses. And I despaired of giving this talk somewhat because I wanted it to be somewhat comprehensive, but everywhere I looked in the ocean circulation and tried to review the wonderful work that's going on now, I found new and more and different and more exciting stories of turbulence shaping circulation. So in that way, I just have to skip through lots of results and come to the end, which is a startling conclusion that we need from this theoretical and dynamical community help. Thank you.
It's a wonderfully succinct thing to say that effective Peckley number for tracer transport along the stratification surfaces should be of order 3 to 5, and it reminds us how terribly different the effective Reynolds number is, and indeed can we speak of such a thing because of the wave turbulence jigsaw puzzle that says that momentum is transported over long ranges by the Rossby wave propagation mechanism. And I'm glad, therefore, you avoided talking about effective Reynolds numbers.
Oh, but you just used that word.
With a warning, a health warning attached.
Well, yes, imaginary Reynolds numbers. Well, I think it was you, Michael, that reminded us, or maybe it was me, I don't know, reminded us that wave stresses make turbulence in the presence of large-scale PV structures make turbulence very non-diffusive in the usual sense, but for momentum,
yeah.
But for these other properties, it's certainly doing its work in the Peckley number sense. That's right. Yeah.
Your picture of the I enjoyed the video of the vortices and so on, and the El Nino. But what was interesting was that I visited Jim Williams' lab in March and saw these very precise computations of the flow coming up the western side of South America and then breaking away, and then you brought up all this deep water, and that was the sort of cool La Nina kind of phenomenon. But yours was showing very little sort of dynamical activity in that current coming up the west side of South America. Absolutely very little was compared with all the action on the east side and so on. And I just wondered whether that was vorticity and not temperature, of course, wasn't it? You were showing.
That was elevation. It was pressure, you might say.
Yes.
So, one really should sit with a better screen and a lot of time to look at that, and you would see a lot of the things you're looking for. I think the eye is caught by the most intense elevations in sight, and also the spatial resolution. There's a filter at work here where we're missing out on some of the smaller spatial length scales. But if you look hard and zoom in on those pictures, I think you'll see what you're looking for. And I did point to the annual Rossby waves, which are being transmitted westward from the boundaries of the ocean and breaking into these solitary Rossby waves. Those, when we examine them close in, they're very, very well recorded by this method, actually. I mean, the altimeter has a problem very near the coast, but those structures there. I think you might be missing out on the really coastal phenomenon.
There was a parliamentary question on El Nino, by the way, and Ted Heath blamed British inflation in the early 70s on El Nino because he said that it was a marvelous interaction in which he said that it was the cause of the rise in price of sardines used for cattle feed, and these were all dying off South America because the waters were hot, and you can imagine the opposition were not completely persuaded by this or the esoteric explanation of economics.
That's the teleconnection I didn't know about.
Maybe time for one more question.
Well, going back to the kind of mundane, I mean, you showed the nice picture of the movie of the sea surface height patterns, and you emphasised the westward propagation. But to what extent do you think that that's affected by the spatial filtering? I mean, if you were able to see the kind of Lagrangian coherent structures, would there be more of a sense of eastward propagation in those things like the Kuroshio and the Gulf Stream? That's
a very interesting question. There certainly is some of that, some eastward moving features which you could track. But it's surprising actually in the separated western boundary currents how actually their phase is only slowly doing that. There's a lot of standing wave energy in those currents, and they are flinging off rings north and south, which you know about, but they're certainly not guns shooting eddies eastward in that sense. Yeah, I mean, so I think to some extent, yes, but I don't think it's terribly misleading what you saw.
Okay.
Thanks.